Hey chemists, how you going? Just want to talk you through subtopic 3.7, which is looking at the ester functional group. So we'll get right into this one. So at this stage, we've looked at a lot of different functional groups in organic chemistry. The ester functional group is the one that we're focusing on today. So we're going to be looking at naming esters, their structure, and how the skeletal formula is represented. A detailed method of preparation, and I'm going to refer you to another video to watch an actual experiment in action. And we're going to be looking at some reactions with esters, including alkaline and acidic hydrolysis reactions. So ester functional groups contain the condensed structural formula of COO, and this is how it looks in the extended structural formula. So you've got a C double bond O carbonyl and an oxygen attached, and you've got two hydrocarbon side chains coming off. Okay, so this is a non-terminal functional group. It's in the middle of a molecule. In order to name an ester, there's two different molecules that combine to form an ester. So one part is from an alcohol and one part is from a carboxylic acid. When you name an ester, the alcohol part is named first, and that suffix is -yl. And then the carboxylic acid part is named second, and the ending of that is -08. So how esters are prepared? From a condensation reaction between alcohols and carboxylic acids. So condensation reactions produce water as a small molecule coming off. So an example of that is ethanol as your alcohol and propanoic acid as your carboxylic acid. So hopefully you can identify those alcohol and those carboxylic acid functional groups pretty quickly. Now, when you're drawing a reaction, it's always good to have the alcohol and the carboxylic acid functional groups side by side so you can easily have the water dropping off. So the water is highlighted here, that's going to fall off. And what you end up with is the O combining with this carbon to form this ester functional group here. And that is called ethyl propanoate. So ethanol becomes ethyl, propanoic acid becomes propanoate. So remember, the naming convention is from the alcohol first and then the carboxylic acid next. So the skeletal structure can be observed like this. Now, this is our ester, and when you are trying to identify the constituents of your ester, so you want to have an ester and you want to break it up into the carboxylic acid and the alcohol, you want to basically get your ester functional group and just imagine a line cut through the middle there. Now, you can draw that as well, just kind of chop that up to help you visualize what's happening. A H attaches itself to this oxygen in order to make the alcohol. So this oxygen is from the alcohol, and then you add an OH to this carbonyl to make the carboxylic acid. And then you can do your normal conventions to try and figure out what the carboxylic acid and the alcohol were. So I've numbered the carbons here. Carbon number 1, carbon number 2, carbon number 3. So that would be prop. So it's going to be propanoic acid. And then this alcohol, 1, 2 carbons. So that's going to be F. So that's going to be ethanol. Okay. So some examples of esters. Methyl ethanoate. So again, you want to identify that it's an ester, looking at this functional group here. And then you look at this oxygen, and then you count the number of carbons, and that's the alcohol component. So 1 carbon would be meth, and then, so that makes methyl. And then the other side, you've got 1, 2 carbons from the carboxylic acid, so that's ethanoic acid in order to make that. So that's going to be ethanoate. This one here, ester functional group, oxygen side here, that's from your alcohol, so that's methyl, and then 1 carbon from your carboxylic acid side, so it's methanoate. This is propyl ethanoate. So again, here, oxygen, 3 carbons makes propyl, and then 2 carbons, ethanoate. And this is butyl methanoate. So you can see the representation of the ester looks a bit different in the skeletal form. So you just want to familiarize yourself with these oxygens side by side, which is how you identify your ester. So in order to draw the following esters, you want to get some practice in order to represent different structures. So ethyl pentanoate, you'll need to be able to draw this from just the description itself. Okay, so you want to basically start by drawing this, and then the ethyl, that's how many carbons come off of this oxygen here. So ethyl is 2 carbons, 1, 2. And then pentanoate, that's the carboxylic acid side. So basically that's here. Remember to include this carbon, 1, 2, 3, 4, 5. And this is propylbutanoate. You can see different representations here. Condensed structural formula here. We've got full structural formula here where you can see all the hydrogens coming off, and you've got the skeletal structure here. And your essentials book and the work that I'm going to set you guys has more practice doing naming. So products of esters. Aspirin is the product of an ester. It's used to relieve pain and reduce inflammation, and it's an ester of salicylic acid and acetic acid. Oil of wintergreen is an oil that's used to soothe muscles, and it's an ester of salicylic acid and methanol. I was going to show a few more esters and basically what they do. So all of these have, esters are responsible for, I guess, fruity scents and smells. So lots of different kinds here. Buttery kind of smells here. Banana, blackberry, oil of wintergreen, like I said before, citrus fruits, peach, pineapple smells, cinnamon, raspberry, lavender. You can see rum, strawberry, apple is a pretty easy one to make. So there's lots of different examples. These are all esters. You can see the ester functional group in all of them. They're responsible for fruity smells, which is pretty cool. So that can be produced synthetically. So we can add like banana smells to a banana candy or something like that. So esters give flowers and fruits their pleasant fragrances and flavors, as I've just kind of identified. So there's a few other examples here, just in a different representation: pears, bananas, oranges, pineapples, and apricots. In order to produce an ester, there's a chemical process called esterification, okay, or Fischer esterification. And I'll link you to another video to kind of show this in action. So Fischer esterification is, I guess, the simplest method of esterification. It's better for short chain hydrocarbons. Once they get a bit bigger, this process doesn't work as well. You want a strong acidic catalyst, which increases the rate of reaction, like sulfuric acid. It's a reversible reaction. There's an equilibrium that's established after a few hours. So the alcohol and the carboxylic acid and the ester and the water is an equilibrium reaction. The Kc value, which is which side of the equilibrium is favored, it varies with temperature, but it's less than 1. So basically, it favors the formation of reactants. So the yield of ester is usually relatively low. There are some things that we can do though to increase the yield. One methodology is to increase the concentration of alcohol that's being used, which will shift the equilibrium to the product side. So the rate of formation of an ester is very slow, even with a catalyst. So what we need to do is we need to heat under what's called reflux. So this is the setup for reflux. So you have a heat source, you have a flask, this is a pear-shaped flask, and you have a condenser sitting up the top. So the condenser cools the vapor down. So essentially what's happening here is this will gently boil. You want to have gentle boiling, and some vapor is going to come up and hit that condenser, and then it's going to go back down. Okay. How do we increase the rate of reaction? We increase the temperature, so that's why we do this. But we don't want to lose any product, which is why the reflux is utilized. Reflux needs to be controlled, so low. Otherwise, the reactants can boil and escape if the boiling is too vigorous, and you can get low yield of product. Reflux allows the reaction to occur continuously, and there's no loss of reactants or products from the reaction vessel, which is important because we don't want to lose our product, which lowers yield. So the reaction mixture is your alcohol, your carboxylic acid, and your strong acid catalyst. An example practical for an ester: ethanol propanoic acid makes ethyl propanoate, and water. So after 45 minutes, you reflux, you want about half an hour, 45 minutes. What's present in here? We've got our products, which is our ester and water. We've got our reactants, which is ethanol and propanoic acid, because remember, it's an equilibrium reaction, so you're not going to get 100% product. And our catalyst, because that doesn't get consumed in the reaction. So there's 5 things in this flask at the moment. Once the reflux is finished and that reaction cools down, you're going to get 2 separate layers. The organic layer is going to contain ester and propanoic acid. So organic is non-polar. Our aqueous layer is going to be water, sulfuric acid, and ethanol, which is a short chain alcohol, polar, mixes with water. So now what you want to do is you want to pour some water into the separating funnel. So this piece of glassware here, and to dissolve more water-soluble components, and also to see what layer is the aqueous layer. The aqueous layer in this example is more dense, so it's going to be in the bottom. So I've represented that here. So water layer, organic layer. The important thing is to recognize what layer is actually important for our practical. What do we want? And that's the organic layer because it has the ester dissolved. What you do then is stopper the separating funnel and shake it to mix. Let it settle. You're going to get 2 layers settled out. We want the organic layer, as I mentioned. You discard the aqueous layer into a small beaker. You don't want to get rid of it down the sink or anything like that. You don't want to dispose of it because just in case you make a mistake, you want to leave it there. And you also want to wash the organic layer a few times. So you're left with this organic layer here, which is what we want. We add a sodium carbonate wash. We stopper that. You're going to get effervescence because there's sulfuric acid left over. There's going to be some remnants of that left over. You release the carbon dioxide due to pressure buildup. So you want to do that pretty quickly because otherwise you can get a lot of pressure and you can have some accidents occurring there. So in order to do that, you put your thumb over the stopper, open the seal and let the carbon dioxide out, and you do that a few times. So basically, shake, let go, shake, let go. You pour the organic layer into a small conical flask. It probably has a cloudy appearance. You add fused calcium chloride, kind of like lumps of chalk. That's called a drying agent. So that's going to absorb all of the leftover water. Swell the flask. We've got almost 99% ester. So the next thing is the hydrolysis of an ester, which is kind of the reverse of what we've just done. So condensation is to make an ester. Hydrolysis is to break up an ester into its original. So you can do this in acidic conditions or basic conditions. In acidic conditions, you're going to get a carboxylic acid and alcohol product. In basic conditions, you're going to get a carboxylate ion and alcohol product. So you mix an ester with a strong acid or a strong alkali. You heat the mixture under reflux, and you can break this up again. So I've just got examples for alkaline and acidic hydrolysis of ethyl methanoate. So guys, what we've gone through is the structure of esters, the naming of esters, the practical in order to produce an ester, and then the reactions involved or how it looks when we break up an ester. Thanks for watching and good luck with your theory.